Welcome to Drift into Quiet Knowing. Tonight we'll step into one of the deepest, most beautiful, and most easily misunderstood ideas in astronomy. Whether the Big Bang was truly an explosion in space. In the familiar version we often imagine, there is an endless darkness, and then, in the middle of that darkness, a tiny point of light appears, bursts violently outward, and sends matter flying in every direction, like a cosmic firework. But that image, powerful as it may be, is not how modern science understands the hot, dense beginning of the universe. If the Big Bang were an ordinary explosion, we would have to ask, where did it explode? Where was its centre? And what point are the galaxies flying away from? But when astronomers observe the universe, they do not find a single centre. There is no special place in the sky from which everything was launched like fragments of debris. Instead, what we see is that the distances between faraway galaxies are growing larger over time. Not because everything is racing through a pre-existing empty space, but because space itself, the space between them, is expanding. On this journey, you will understand why the Big Bang was not matter exploding into space, but the expansion of space itself. You will see why every place in the universe today can be thought of as a place where the Big Bang once happened. And you will meet the ancient light left over from when the universe was young, a light that has cooled, stretched, and still quietly covers the sky all around us. Now let us begin with the most important point. When people hear the words Big Bang, almost everyone imagines an explosion. An explosion so enormous that nothing could possibly be bigger. A blazing ball of fire in the darkness, flaring up, bursting apart, and throwing matter in every direction. That image is easy to remember, powerful, and very cinematic. But precisely because it is so easy to picture, it can also lead us in the wrong direction. In an ordinary explosion, there are always three things: a place where the explosion happens, an object that explodes, and surrounding space for the fragments to fly into. A firework exploding in the sky needs the sky around it. A bomb exploding on the ground needs air, soil, pressure, and space for the shockwave to spread through. But when we talk about the Big Bang, we cannot simply take that everyday experience and enlarge it to the size of the universe. The subtle point is this: the Big Bang was not an object sitting inside space and then exploding. The Big Bang is the name we use for the very early state of the universe, when the entire observable universe we see today was once much hotter, much denser, and the distances within space were far smaller. In other words, what was changing was not just matter moving through space. The very structure of distance in space was changing. If we imagine space as a stage, then in an ordinary explosion the actors run across the stage. But in an expanding universe, the stage itself is stretching. This is why the image of an explosion in space is not accurate enough. It makes us think there was already a vast empty space, and then the universe suddenly appeared and blasted itself into that emptiness. But modern science does not need such a pre-existing emptiness in order to describe the expansion of the universe. When an astronomer says the universe is expanding, they do not mean that every galaxy is flying through space like shrapnel. In smaller regions, such as inside a galaxy, or inside a group of galaxies held tightly together by gravity, gravity can still overcome the overall expansion. Earth is not expanding. The solar system is not being stretched apart. The Milky Way is not dissolving because space is growing. But on very large scales, between distant galaxy clusters, we observe a profound pattern. The farther away a galaxy is, the more its light is stretched toward the red, as though the space between us and that galaxy has expanded while the light was travelling through it. Light, across a journey of billions of years, is like a thin thread being stretched along with space. Its wavelength grows longer, its colour shifts toward the red, and in that very small change, the universe reveals that it is not standing still. If the Big Bang were a normal explosion, we could do something very simple in our imagination. Rewind the movie. The fragments flying outward, when rewound, would return to a single point. That point would be the centre of the explosion. But the universe does not give us a centre like that. When we look very far away in every direction, we do not see one side that is more special than the other, in the sense of, that is where the explosion began. There is no central burn mark in the sky. There is no single direction from which every galaxy is moving away. Instead, every observer in any galaxy far enough away from local motions can see other distant galaxies appearing to move away from them. This does not mean every place is the centre in the ordinary sense. It means the centre of an explosion model no longer fits. A gentle way to see this is to think of the surface of a balloon being inflated. Imagine only tiny beings living on the surface of the balloon, and they know nothing about the space outside or inside the balloon. To them, the world is only the two-dimensional surface. As the balloon expands, every point on the surface moves farther from the other points. A being standing anywhere would see more distant points receding, but on that surface itself, no point is the centre of the expansion. The centre of the balloon lies outside the surface, but for beings who live only on the surface, that centre is not part of their space. This image is not perfect, because the real universe does not necessarily have to be the surface of a three-dimensional balloon in any simple sense, but it helps us loosen one knot. A space can expand without needing a centre located inside that space itself. Another image closer to everyday life is a loaf of raisin bread rising in an oven. The raisins are inside the dough. As the dough rises, the distances between the raisins increase. If one raisin could observe, it would see the other raisins moving away from it. The farther a raisin is, the faster the distance increases. But that raisin is not the centre of the loaf in any special sense. Every raisin could feel something similar. What matters in this image is not that the loaf has an edge, or that there is an oven outside it. Those are just limits of the example. What matters is that the distances between points increase, because the medium containing them is expanding. With the universe, the core idea is the same. Distant galaxies do not need to fly outward from the centre of an explosion. The distance between large regions of space is increasing. We need to be careful here, because every example can become a trap if we believe it too literally. A balloon has an outside, a loaf of bread has an edge, but the universe does not necessarily have an outside in that sense. When we ask, what is the universe expanding into, we may be using a habit of the mind more than asking a clear physical question. In everyday life, everything that expands into its surroundings. Steam expands into the air, smoke spreads through a room, water waves move across a lake. So our minds automatically ask what the universe is expanding into. But in general relativity, space is not just a passive box that contains matter. Space and time are part of the geometry of the universe. They can curve, stretch, and evolve over time. So the expansion of the universe does not necessarily need a larger room to contain it. We are not standing outside the universe watching it swell. We are inside that story. This is what makes the original question deeper. If the Big Bang did not explode in space, then where did it happen? The answer sounds very strange at first, but it is faithful to the modern model. It happened everywhere. Not everywhere like a fire spreading from one point to another. Rather, every place today in the observable universe was once part of that hotter, denser state. The room where you are lying down, the planet beneath our feet, the sun, the Milky Way, the distant galaxies seen through telescopes, all of them are not fragments flying out from some strange faraway point. They are parts of a universe that expanded together. If we rewind the history of expansion, we do not return to a point in present-day space. We return to a time when all observable space had much greater density and temperature. This is very different from how an explosion works. When a firework explodes, matter is pushed through the air from a specific location. After the explosion, there are regions near the centre, regions far from the centre, this direction, that direction, faster fragments, slower fragments. The explosion leaves behind a structure that can be traced back to its original location. But cosmic expansion is not matter blasting through a still background of space. It is more like a change in the ruler used to measure distance. Two galaxy clusters may not be firing engines to run away from each other. Space between them increases, and the result is that the distance grows. Say it very slowly, matter is not exploding into space. Space itself between regions of matter is expanding. That is the one key takeaway of this entire journey. We should also talk about the word bang in another sense, sound. An explosion in everyday life creates pressure waves that travel through air. We hear them because the air is compressed and stretched, striking the eardrum. But the Big Bang was not a sound that someone standing outside could have heard. There was no outside observer. There was no cosmic atmosphere to carry a giant boom in the ordinary sense. The early universe certainly had density fluctuations, waves in hot plasma, and real pressure changes in the material environment of that time. But that was not a cinematic explosion echoing through empty space. It was the physics of a young, hot, dense universe, where light and matter interacted continuously. When we call it the Big Bang, we are using a historical name, not an audio recording of the first moment. What makes science beautiful is that it forces us to replace a simple image with a more accurate one. And the more accurate image is often quieter. We do not need to imagine a fireball splashing through darkness. We can imagine a very young universe, almost uniform on large scales, hot enough that atoms could not yet exist stably, where matter and radiation were blended in a dense state. Then, as space expanded, the universe gradually cooled. It didn't cool because heat poured outward into a colder, empty region. It cooled because expansion changed the energy of radiation and the state of matter. Light was stretched, temperature fell, physical conditions changed. From there, new stages of the universe could begin to appear. If we look only through everyday intuition, this sentence sounds almost impossible. Every place was once closer together. But in cosmology, closer together does not mean everything was inside a tiny point within a larger room. It means the scale factor of space was smaller. The distances we measure today between distant regions were once much smaller in the past. When we say the observable universe was once in an extremely hot and extremely dense state, we're talking about the entire part of the universe that light can tell us about, not a small ball exploding in some corner of infinite emptiness. This way of speaking requires patience, because it does not give the imagination an easy picture to draw. But it gives us something more valuable, a picture closer to the evidence. The first evidence comes from the expansion observed through the light of galaxies. When light from distant galaxies reaches us, its wavelength is usually stretched. In many cases, this stretching fits the picture that space expanded while the light was travelling. If the universe were absolutely still, we would not expect to see such a general pattern on large scales. But as astronomers look deeper and farther, they find that the universe has a history. It is not an unchanging stage. It has a hotter and denser past. It has evolution. Galaxies are not just sitting there like lamps hanging from a ceiling. They belong to a space with a dynamic history. The second piece of evidence is the ancient light covering the entire sky, the cosmic microwave background. We will go deeper into it later, but even here it helps us understand why the Big Bang is not like an explosion with a direction. If the Big Bang were an explosion at one specific place, we might expect the leftover heat to be stronger from one particular direction. But the cosmic microwave background comes from every direction with extremely high uniformity, with only tiny fluctuations. It is like a thermal afterglow from the young universe, not a trail of smoke from one corner of the sky. The sky, in every direction, carries traces of the time when the universe was hot and dense. This fits much better with the idea that the Big Bang was the early state of the entire observable universe, not a local explosion. Here, we meet a truth that is both simple and silencing. You cannot point toward the Big Bang in the sky. There is no star marking, that is where everything began. There is no galaxy playing the role of the first crater. Every direction we look deeply is a direction looking into the past. The farther we look, the longer ago the light left its source. And when we look far enough, we do not see the edge of the explosion. We approach the time when the universe was still opaque, before light could travel freely through space. The night sky, then, is not only space. It is time spread out before our eyes. Every point of light is a late-arriving letter. Every distant galaxy is an image of the past. And that entire history does not need the centre of an explosion in order to be real. Let us pause for a moment with the uneasy feeling this idea can create. The human mind likes centres. We like to ask what is in the middle, what came before, what is outermost. When we look at a circle, we look for its centre. When we see an explosion, we look for the starting point. When we hear a story, we want a clear stage. But the universe does not have to fit our storytelling habits. Some questions in cosmology are not wrong because they are foolish, but because they carry hidden assumptions. The question, where did the Big Bang explode, carries the assumption that there was already a space in which the Big Bang was a local event. Once we let go of that assumption, the question changes. We no longer ask, where did it explode, but what state did the universe expand from? How did distances change? And what traces remain that allow us to test that idea? This is how science matures. It does not only answer questions, it sometimes corrects the questions. If someone asks where north of the North Pole is, we do not answer by pointing in a new direction. We explain that at the North Pole, the usual meaning of north has reached its limit. In a similar way, when we ask what the universe is expanding into, we may be pulling a familiar concept beyond the place where it still works. That does not mean the question is completely meaningless. It only means we have to be more careful with language. Space in cosmology is not like an empty box in a warehouse. It is part of the physical model itself. And when the model says space expands, it is talking about a change in geometry, not a ball of matter swelling into an outside room. There is one more point to make clear. Saying the Big Bang was not an explosion in space does not mean the Big Bang is vague or unsupported by evidence. On the contrary, the Big Bang model is one of the most powerful explanatory frameworks in modern science because it connects many different observations into one consistent story. The expansion of the universe, the cosmic microwave background, the proportions of light elements such as hydrogen and helium, the formation of large-scale structures such as galaxies and galaxy clusters, all fit the idea that the universe was once hotter and denser. But hotter and denser does not mean a fireball sitting inside empty space. That is where many people slip. They hear hot and dense and automatically place it inside a cosmic room. Science is more subtle. The space of that room itself is part of the story. When we think this way, the image of the Big Bang becomes less noisy but more profound. It is no longer the opening scene of a cosmic action movie. It is more like realizing that the entire fabric of reality was once in a different state. The space between galaxies today, the space light is traveling through, the space telescopes measure, all of it carries the history of expansion. Distance is not something unchanging, it has a past. And when distance has a past, light also carries traces of that past in its color, in its wavelength, and in the remaining temperature of the sky. Imagine you're standing in a dark room, and on the ceiling are points of light very far away. If the room is still space, and the lights are flying away from one point on their own, we could trace their paths. But if the very background of the room is stretching, then every distance changes in a different way. You cannot simply look at things moving farther apart and conclude that there is a bomb in the middle. You have to ask, is the object moving, or is the ruler between objects changing? In the real universe, both can exist at different levels. Galaxies have their own motions caused by gravity, but on the larger scales, the dominant picture is the expansion of space. This changes how we understand every path taken by light, and that is why the sentence "the Big Bang happened everywhere" is not poetry. It is a short way of expressing a physical idea. Every place in the observable universe today was once part of the hot, dense, early universe. It is not that every place received fragments from a center, but that every place belongs to the same history of expansion. When you look at your own hand, the atoms inside it were not thrown out like ash from some distant explosion. They are the result of a much longer chain of history. The universe cooled, light nuclei formed, stars were born, stars created heavier elements, gas clouds formed new star systems, planets formed, and complex chemistry gradually appeared. But the deepest stage beneath that entire sequence is a universe that was once hotter, denser, and then expanded. This also helps us avoid another misunderstanding. The Big Bang does not say that all galaxies today were once stacked on top of one another in present-day space, like objects compressed inside a small box. Present-day space is not a box that existed from the beginning. When we rewind the model, we are rewinding the expansion factor of space. Distances between regions shrink, density rises, temperature rises. But the phrase "everything was in a single point" can be dangerous if we understand it as a tiny point located somewhere. In physics, when we go too close to the very first moment, our current equations can reach their limits. General relativity shows a trend toward an extreme state, but to describe the very earliest moment precisely, we may need a theory of quantum gravity that humans have not yet completed. So a careful scientist will not turn the unknown into a story that sounds too certain. That caution does not make the story less beautiful. On the contrary, it makes the beauty more real. We know the universe is expanding. We know it was once hotter and denser. We have ancient light as a witness. We have the distribution of elements and large-scale structure as witnesses. But we do not need to overstate things by saying we have seen the moment of absolute zero. Science is like someone walking through the night with a good lamp. The light reaches very far, but it also shows us where the darkness begins. And in the story of the Big Bang, that darkness is not a failure. It is a reminder that the universe is larger than any simple image we build in our minds. So from now on, when you hear someone say the universe exploded out of nothing, remember that the sentence may be appealing, but it is not precise enough. A statement closer to science would be this: the observable universe was once in a hotter, denser state, and from that state space expanded, causing cosmic distances to increase over time. There is no single center of explosion. There is no edge of a fire wave rushing into an outside emptiness. There is no observer standing outside to hear the blast. There is only a universe writing its own history through expansion, through stretched light, through falling temperature, and through the traces left across the sky. And if this makes you feel small, that is a very fitting feeling. But small does not mean meaningless. On the contrary, it is precisely because we are small that understanding this becomes so extraordinary. A living creature on a small planet, orbiting an ordinary star inside an ordinary galaxy, can still reason that all observable space was once in a hotter and denser state. We do not need to fly outside the universe to look at it from afar. We only need light, mathematics, telescopes, and patience. From the faint red shifts in the spectra of galaxies, from the weak microwave glow spread across the sky, from equations that describe space-time, humans have learned that the beginning of the universe was not like the explosion of an object in a room. It was more like the opening of the room itself. And once we understand that, the original question is no longer simple. Was the Big Bang an explosion in space? No, but it is far stranger than an explosion. An explosion only throws matter outward through space that already exists. The Big Bang, in the modern understanding, leads us to a universe in which space is not a motionless backdrop, but a living part of the story. It can expand, it can carry history, it can stretch light, it can make every observer in any faraway region feel as though they are standing in a universe expanding around them. Not because everyone is at the center, but because there is no center in the usual sense. From here, we can go deeper. If there is no center of explosion, then how do astronomers know the universe was once hot and dense? If the Big Bang did not leave behind fragments flying away from one point, then what traces did it leave? The answer lies in the oldest light we can observe directly, a layer of light so faint that human eyes cannot see it, stretched by expansion into microwaves, and still arriving from every direction in the sky. It does not shout, it does not flash like fireworks, it only whispers steadily and coldly that the universe was once much younger, much hotter, and much closer together. Before we reach the layer of ancient light left over from when the universe was still very young, we need to pause at something that seems simpler, but in truth, it opened the first door to all of modern cosmology. The universe is expanding. This is not just a beautiful idea. It is not a poetic metaphor for saying that everything is changing. It is a conclusion drawn from real light, from real spectral lines, from real galaxies lying millions and billions of light years away from us. When an astronomer says the universe is expanding, they are not saying it because the imagination enjoys a grand story. They are saying it because the light from distant galaxies has carried that trace with it on its journey to the lenses of our telescopes. In everyday life, when two objects move away from each other, we usually think one object is moving away from the other. A car leaves a station, a ship sails away from the shore, a person steps backward across a room. All of this happens inside space that already exists. Space is like the floor, and objects are the things moving across that floor. But on the scale of the universe, there is a deeper possibility. The floor itself is not standing still. The very ruler that measures distance between faraway regions of the universe is changing. That sounds strange because in daily life we do not see rulers stretching by themselves. But in general relativity, space and time are not a rigid, motionless stage. They are part of physical reality. They can curve, they can change, and in the case of cosmology, they can expand over time. The evidence comes from a phenomenon called cosmological redshift. Imagine light as a chain of waves. Each color corresponds to a different wavelength. Blue light has a shorter wavelength than red light. When light travels through an expanding universe, the space along its path stretches, and the light waves are stretched along with it. A wave that was once shorter gradually becomes longer. Its color shifts toward the red. This is not light getting tired in any human sense, and it is not losing energy because it is bumping into some invisible layer of dust. It is the trace of light traveling through space that is expanding. Each tiny wavelength becomes a ruler recording the history of distance. The subtle point is that astronomers do not see just a few galaxies whose light is redshifted. On large scales, they see a pattern. The farther away galaxies are, the greater their redshift usually is. In more familiar language, the farther away a galaxy is, the faster it appears to be moving away. If only a few objects behaved this way, we might think they were moving individually. But when that pattern appears across the wide sky, in many directions, it suggests something else. The space between galaxy clusters is increasing. This recession is not like fragments flying away from an explosion with a center. It is more like all large distances in the universe being multiplied over time. We can picture this with a rubber band marked with ink dots. If you stretch the rubber band, the ink dots move away from one another. No dot needs to crawl across the rubber by itself. The distance increases because the material between them is being stretched. If you stood at one dot and looked only at the other dots, you would see all of them moving away from you. The farther dot would move away faster, not because it has a stronger engine, but because there is more stretching rubber between you and it. Of course, the rubber band is only a one-dimensional example, while the real universe is far more profound. But it helps us hold on to the main idea. When space expands, the distance between faraway regions increases without requiring a single center of explosion. And this is where our intuition is very easy to fool. If every distant galaxy appears to be moving away from us, we might imagine that we are at the center. But that is the wrong conclusion, like one dot on the rubber band thinking it is the center simply because it sees the other dots moving away. An observer in a very distant galaxy would see the same thing. From their point of view, other galaxies would also be moving away, not because their galaxy is the true center, and not because our galaxy is the true center, but because the expansion of space makes every observer in the large cosmic flow see an almost similar picture. The universe does not hand the throne of the center to any special place. Think again of the image of raisin bread rising, but this time let us use it carefully. The raisins do not shoot through the dough like bullets. They sit inside the dough. As the dough rises, the distances between them increase. One raisin looking at the others would see them moving away. A farther raisin may increase its distance faster, because there is more rising dough between the two raisins, but no raisin is the single place where the loaf began to rise. What we need to keep from this image is not that the loaf has an edge, an oven, or air outside it. Those are extra details that can mislead us. What we need to keep is this. Distance does not have to increase because everything is shot outward from a central point. Distance can increase because the background holding those things is expanding. If you notice, all of these examples are protecting one single message. The Big Bang was not an explosion in space. The expansion we observe today does not look like the trace of a cosmic bomb with a center. It looks like the continuation of a history in which space itself once had greater density, higher temperature, and smaller distances. When we rewind the expansion, we do not search for some point in the sky where all galaxies once came out. We go back to a state of the entire observable universe, where every region we see today was once much closer together. This is the difference between a cinematic image and a scientific model. One important thing to say is that expansion does not act the same way on every scale. In your room, objects are not being pulled away from one another because the universe is expanding. Your body is not expanding. Earth is not growing larger because space is expanding. The solar system is not being torn apart. Even the Milky Way is not simply swelling along with the general expansion. The reason is that on smaller scales, electromagnetic forces, nuclear forces, and local gravity hold structures together. A table is held together by electromagnetic forces between atoms. Earth is held together by its own gravity. The solar system is held together by the sun's gravity. The Milky Way is held together by the gravity of the mass inside the galaxy, including dark matter. Cosmic expansion becomes clearest at enormous distances between galaxy clusters that are not tightly bound to each other by gravity. This is very important. because without making it clear, listeners might imagine the universe expanding like a rubber sheet stretching everything on it, making even atoms grow larger. That is not what happens. Local bound systems do not follow the general expansion in that way. The Andromeda Galaxy, for example, is moving toward the Milky Way because of the local gravity between the two galaxies within the local group. That does not disprove the expansion of the universe. It only shows that many kinds of motion overlap in the universe. There is individual motion caused by nearby gravity. There is the general flow of expansion on large scales. When we look at galaxies far enough away, beyond the strong influence of the local group, the expansion picture becomes clearer, like seeing the main current of the ocean from high above instead of focusing on each small ripple. We can compare it to a wide river. On the surface are leaves, foam, and small branches. A leaf may spin in a small eddy, drift backward for a moment, bump into another branch, or be pushed sideways by the wind. If we look only at one leaf near the bank, we do not understand the river. But when we look at the whole surface from above, we see the main flow. The universe is similar. A nearby galaxy may move toward us. A group of galaxies may be pulled together by gravity. But on very large scales, the general pattern shows that the space between faraway regions is expanding. Nearby exceptions do not break the larger picture. They make the picture more real, because the universe is not a perfectly smooth model with no details. That expansion also has a beautiful consequence. When we look far away, we also look back in time. Light does not arrive instantly. Light from the moon takes a little more than 1 second to reach our eyes. Light from the sun takes a little more than 8 minutes. Light from nearby stars may take many years. Light from distant galaxies may take millions or billions of years. So a telescope is not only a machine for looking far into space, it is also a machine for looking deep into time. A galaxy 10 billion light-years away, if observed, does not appear as it is right now in the everyday sense. It appears as it was when its light left it in the distant past. The night sky is an archive of time, where each photon is a late messenger. But here there is another point that is easy to misunderstand. If the universe is about 13.8 billion years old, why can we say the observable universe has a radius greater than 13.8 billion light-years? The reason is that while light was travelling, space was also expanding. A photon may begin its journey from a very distant region when the universe was young. During the entire time it travels toward us, the distance between us and the region that emitted the light continues to grow. So the current distance to the place that emitted the light can be much greater than the time the light has travelled multiplied by the speed of light in our simple intuition. This does not mean the object flew through space faster than light in a local sense. It means the distance between faraway regions of space increased in an expanding universe. Once again, the essential point remains: space is not just an empty background, it participates in history. When you look up at the night sky, you're not seeing all of reality. You're seeing the part of the universe whose light has had time to send us its message. That part is called the observable universe. It is not necessarily the entire universe. It is the limit of what can be observed from our position at this moment. Because light needs time to travel, and the universe has a finite age. If there are farther regions whose light has not had enough time to reach us, they may still exist, but we cannot see them directly yet. So when we say we are at the center of the observable universe, that does not mean we are at the center of the whole universe. It is like standing in the middle of a circle of fog. You are at the center of the region you can see, not the center of the entire world. The image of a person standing in fog is very useful. If you stand in a fog-covered field, you can see a circle of space around you. The edge of the visible region moves with you. Someone else standing some distance away has their own visible circle. Each person is the center of their own observable region, but no one becomes the true center of the field because of that. The observable universe is somewhat similar, only far more profound. Its limit is not ordinary fog, but a limit created by the speed of light, the age of the universe, the history of expansion, and the physical state of the early universe. Each observer in a distant galaxy would have their own observable universe, partly overlapping with ours and different in the farthest regions. That reduces the feeling that we are the center, but it increases the beauty of the principle. There is no absolutely privileged position. This returns directly to the question of the Big Bang. If the observable universe has us in the middle in an observational sense, it is very easy to draw a sphere around us and imagine that we are at the center of everything. But that is only the center of what we can see, not the center of birth. It is like turning on a lamp in a dark room. The lit region around you has you in the middle. But the room was not necessarily built around you. The observational limit is the limit of information reaching us, not a sign that the universe began where we stand. When we understand this, we avoid a subtle mistake, confusing the center of observation with a physical center. The universe can give each observer their own horizon without needing one shared center. Expansion also explains why light from distant galaxies can become redder, fainter, and marked by time. A photon leaves a galaxy when the universe was younger. It begins its journey in space of a different size, travels through a universe that continues to expand, and finally reaches a telescope. In that process, its wavelength grows longer. Each photon is like a thin thread stretched along with the fabric of space. When we measure that stretching, we're not only measuring color, we are measuring part of the universe's history. A galaxy's spectrum becomes a silent record. How much expansion this light has traveled through, how much younger the universe was when it left its source, and what it is telling us about the distance between galaxies. Here, science does not rely on only one kind of observation. Astronomers use many methods to build the cosmic distance ladder: variable stars, supernovae, apparent brightness, spectra, and many other tools. Each method has limits and uncertainties, but when they all point toward an expanding picture, scientific confidence becomes stronger. What matters is not one perfect measurement, but the convergence of many different traces. An investigator does not rely on a single footprint. They look at the direction of travel, the depth of the footprint, the dirt on the shoe, the timing, the light, and many other details. Cosmology is the same. Expansion is not a slogan. It is the result of many layers of evidence placed on top of one another. Even so, saying that the universe is expanding does not mean every question is finished. What exactly is the expansion rate? How has it changed over time? Why does the expansion today seem to be accelerating? What roles do dark matter and dark energy play in the whole picture? These questions are still active areas of research, but what remains unknown does not weaken the main point of this section. Even as the details are still being measured more precisely, the background picture remains very strong. The universe is not standing still. Light from distant galaxies reveals expansion, and that expansion does not require a center of explosion somewhere in space. Scientists still debate parameters, deeper mechanisms, and the distant future, but they do not return to the simple image that the entire universe is debris from a bomb sitting in the middle of darkness. One of the things that always makes me feel humbled is the silence of the evidence. Galaxies do not send letters in our language. Light does not explain itself in words. It simply arrives, faint, redder, more stretched, after a journey none of us can fully imagine. Then humans, with lenses, instruments, mathematics, and patience, learn how to read that light. A spectral line shifted slightly, a brightness dimmer than expected, a galaxy as small as a dust mark in a deep image. All of it says the same gentle thing. Distance in the universe has changed. Space has a history, and we are living inside that history. This also makes the idea that every observer sees themselves almost at the center less mysterious. In a universe that is homogeneous and isotropic on large scales, no direction is more special than another, and no location is chosen as the central throne. Homogeneous means that on a large enough scale, the universe looks similar in different places. Isotropic means that from one place, the universe looks similar in different directions. This is not absolute perfection at every small point. Obviously, there are stars, galaxies, voids, and galaxy clusters, but when averaged over very large scales, the picture becomes much more even. This property allows expansion to look as though it is happening around every observer, without requiring a true center. If the universe had an ordinary explosion center, we might expect to see a major asymmetry. One side could look very different from the other. Galaxies might have motion showing that we are off to one side of the debris flow, but the observed picture does not support that image in any simple way. Instead, expansion on large scales is more like a multiplication of distances than a stream of matter from one point. The line between two galaxy clusters grows longer. The line between two other clusters also grows longer. There is no required sign that everything is moving away from some sacred coordinate. The universe is not like a city with a central square. It is more like a map whose scale itself is changing. And when we understand this, we also understand why the question, "Where was the Big Bang?" must be answered very carefully. If we ask it as a spatial address, like asking what street corner an explosion happened on, the question has already chosen the wrong frame. The Big Bang was not a local event inside a universe that already existed. It was the hot, dense, early state of the entire observable universe, and the expansion that followed caused cosmic distances to grow larger. So if we must answer briefly, we say, the Big Bang happened everywhere, because every place today once belonged to that early universe. But the deeper answer is, where is not the most important question. The more important question is, how did the universe expand and how do we know? Notice the change in the way we ask. At first, the mind wants a location. Then science leads us to a history. At first, we want a point of explosion. Then light teaches us about expansion. At first, we imagine galaxies as fragments flying away. Then spectra reveal that the space between them also plays a role. That transformation is a maturing of the imagination. We do not abandon imagination. We train it to move with the evidence. An untrained imagination draws a cosmic bomb. An imagination guided by science sees the ruler of space changing, light being stretched, and every observer having their own horizon. Perhaps this is one of the most peaceful lessons in cosmology. We are not at the center of the universe in a proud sense, but we are not abandoned at the edge of some strange distant explosion either. We are inside the same history of space as every other galaxy. Our position is not special in the sense that the universe revolves around us, but our ability to understand is special in a very human sense. From a small planet, we can read the expansion written across the sky. We can understand that redder light is not only color, but a trace of expanding space. We can understand that the observable universe is not everything, but the region whose letters of light have had time to arrive. And we can understand that no center of explosion needs to be found for the Big Bang to be real. Now, when we look back at the familiar image of an explosion, we can see that it is too small for this story. An explosion has sound, pressure, a central point, fragments, and surrounding environment. Cosmic expansion has geometry, stretched light, observers who are equivalent on large scales, and an observational horizon limited by time. An ordinary explosion ends as energy disperses. The expanding universe continues to write its history through every late arriving photon, every receding galaxy, and every more delicate measurement. If the Big Bang is the first chapter of this story, then expansion is the way those first lines are still being stretched into the present. So when you hear that a distant galaxy is moving away from us, do not rush to imagine it as a fragment flying away from a fireball. Imagine something gentler. The distance between us and that galaxy has grown while its light was travelling. When you hear that every direction shows distant galaxies receding, do not rush to place us at the centre. Remember that an observer far away would see a similar picture. When you hear that the observable universe has a limit, do not imagine that it is the final edge of all reality. Remember that it is the region whose light has had time to arrive, a horizon of information, not the final wall of existence. And from that foundation, we are ready to move toward an even deeper trace. If expansion tells us the universe was once closer together, ancient light tells us the universe was once hotter. If redshift is the trace of space-stretching light, then the cosmic microwave background is the trace of a time when the universe was so young that light and matter had not yet separated the way they have today. It does not come from a star. It does not come from a galaxy. It comes from every direction, like a leftover thermal breath from the early universe. And that layer of light will help us understand even more clearly why the Big Bang was not an explosion in space, but the hot, dense history of space itself expanding. And if that ancient light is coming from every direction, then we have to begin with a powerful truth. The sky does not only contain stars, the sky also contains a layer of light so old that it was born before there were any stars, before there were any galaxies, before the universe had the familiar structures we see today. That light does not shine brightly to human eyes. It does not appear as a band of stars or a glittering cloud. It has cooled dramatically. Its wavelength has been stretched by the expansion of space, and today we detect it mainly as microwaves. But this faint, cold, and almost uniform light is one of the deepest pieces of evidence showing that the Big Bang was not an explosion that happened at one point in space. What is remarkable is that this light does not come from some ancient star. It also does not come from one single first galaxy. It comes from the entire sky. No matter which direction we point our receivers, after removing the light from stars, galaxies, gas, dust, and closer sources, there remains a very faint, very even background radiation, as if the universe is holding a layer of remembered heat within itself. If the Big Bang were a cosmic bomb exploding somewhere, we might expect the leftover trace to be stronger from one special direction, like smoke from a fire drifting out of one corner of the sky. But the cosmic microwave background does not behave that way. It surrounds us from every side. It does not point to a center. It does not say, "Look in that direction, where everything began." It says something far more subtle. The entire observable space was once in a hotter, denser state, and that ancient light was released everywhere when the universe became transparent. To understand why this matters, we need to go back to about 380,000 years after the hot, dense beginning of the universe. That number sounds enormous compared with a human lifetime, but in the nearly 13.8 billion year history of the universe, it was like a very early dawn. At that time, the universe had no stars like the sun. There were no planets, no oceans, no rocks, no living creatures, no eyes to see. Space then contained a hot mixture of charged particles and light. Free electrons were still abundant, and they made it difficult for light to travel far. A photon, meaning a particle of light, would travel only a short distance before being scattered by an electron, changing direction, and then being scattered again. The universe then was like a hot, dense fog, not because it contained water vapor like fog on Earth, but because light was constantly colliding and could not travel freely across large distances. This image of fog is very useful if we use it carefully. When you stand in thick fog, light from a distant lamp is scattered many times by tiny water droplets. You do not see the light source clearly, you only see a blurred glow. The early universe was also not transparent in the way the universe is transparent today. But the cause was not water droplets, it was charged particles. As long as electrons were still drifting freely throughout space, light was constantly being deflected by them. So before that time, if an imaginary observer could somehow exist in those extreme conditions, that observer would not be able to see through the universe the way we see the night sky. The universe was still too hot, too dense, and too opaque to light. Then expansion did what it had been doing from the beginning of the story. It gradually cooled the universe. Not because heat escaped into some cold space outside, but because the expansion of space itself lowered the density and caused radiation to lose energy in the sense that its wavelength was stretched. When the temperature dropped low enough, protons and electrons could combine to form neutral atoms, mainly hydrogen atoms, along with helium and a very small amount of other light elements. When electrons were no longer drifting freely in the same dense numbers as before, light was no longer scattered constantly. The universe suddenly became more transparent. The photons of that time were allowed to travel far. They left the hot plasma fog and began an almost unimaginable journey through expanding space. That light is still here, but it is no longer the hot, glowing light it was when it was released. Across billions of years, space continued to expand, and the wavelengths of those ancient photons were stretched along with it. What was once radiation corresponding to a universe thousands of degrees hot has now cooled to only a few degrees above absolute zero. Because the wavelengths have become so much longer, we do not see it with our eyes as red or yellow light. We detect it with microwave instruments. That is why it is called the cosmic microwave background. The name sounds technical, but its meaning is beautiful. It is the leftover background light from when the universe first became transparent enough for light to pass through. And right here, we begin to see why it strikes at the root of the misunderstanding about the Big Bang. If the Big Bang were an explosion in space, the leftover light would resemble the trace of a local event. We would search for a direction, a center, a special region where the signal was much stronger. But the cosmic microwave background is not a beam of light coming from one side. It is light arriving from every direction, because it was not emitted from an explosion point somewhere in today's universe. It was emitted from every region of the early universe when the entire observable space changed from opaque to transparent. No matter which direction we look, if we look far enough, we are looking back to that very early time, to the final surface where light could separate from matter and travel freely to us. Cosmologists call this layer the surface of last scattering. That phrase sounds like a flat surface or a fixed physical shell, but we should understand it as an observational boundary. It is the collection of places in the past from which ancient photons began their free journey toward us. Because light comes from every direction, we see the surface of last scattering as a layer surrounding our observable universe, but it is not a wall at the edge of the universe. It is also not the edge of an explosion. An observer in another distant galaxy would also have their own surface of last scattering, surrounding their own observable region. This is the same principle that appeared when we talked about the observable universe. Each observer has their own light horizon, but no one becomes the absolute center of the entire universe because of that. The most important thing is not merely that this light exists, it is that this light is almost the same in every direction. When sensitive instruments measure the cosmic microwave background, they find that its temperature is extremely uniform across the entire sky. This uniformity fits the idea that the early universe was once in a hot and dense state on large scales. If it were only a fire or explosion in some corner, it would be difficult to explain why the leftover heat covers the entire sky so evenly. But if the entire observable space was once hot and dense, then expanded and cooled together, a background radiation covering every direction becomes much more natural. It is as if the whole universe was once the furnace, not as if there was a furnace placed at the center of the universe. However, the cosmic microwave background is not perfectly smooth, and that imperfect smoothness is the most precious part. Precise maps show that within this almost uniform background radiation, there are extremely tiny temperature differences. They are so small that, in everyday terms, they are almost impossible to imagine. But for cosmology, those tiny ripples are golden information. They reflect very small differences in density in the early universe. A place that was slightly denser could pull in more matter through gravity. Over a very long time, those tiny differences grew into the large-scale web of structure. Galaxies, galaxy clusters, and enormous filaments of matter stretching through space. If the cosmic microwave background were perfectly smooth, the universe could have been very different. A universe so perfectly even that no place was denser than any other would not easily create gravitational seeds for matter to gather. Without slightly denser regions, matter would have difficulty beginning to clump into large structures. Without large structures, there would be no galaxies. Without galaxies, there would be no generations of stars producing heavy elements. Without those elements, there would be no rocky planets, no complex chemistry, no living bodies, and no person lying quietly at night listening to this story. So the tiny ripples in ancient light are not just noise on a map. They are the earliest fingerprints of a universe uneven enough to become rich. We can imagine the cosmic microwave background as a baby picture of the universe, not a picture of galaxies because there were no galaxies yet, not a picture of the first stars because there were no stars yet. It is a picture of the universe just after it became transparent, carrying within it tiny differences that had not yet bloomed into form. When scientists look at that picture, they do not see faces or familiar outlines. They see the distribution of temperature, regions slightly warmer, regions slightly colder, statistical patterns across the whole sky. From those patterns, they infer the composition of the universe, the geometry of the universe, the age of the universe, and the initial conditions that allowed structure to form. One faint layer of light has become an archive deeper than any text humans have ever written. The history of discovering this light is also memorable, because it shows that science sometimes finds something enormous inside a small noise. In the middle of the 20th century, physicists predicted that if the universe had once been hot and dense, then a cooled background radiation from that era should remain. Later, two scientists working with a radio antenna detected a background signal they could not remove. Even though they tried to find its cause in the instrument, in the surrounding environment, and in ordinary sources of interference, the signal remained. It came from almost every direction. Later, that signal was understood to be the cosmic microwave background. Something that once seemed like annoying noise in a device became one of the greatest pieces of evidence for modern cosmology. But if we stop only at the discovery story, we miss the deepest part. The deepest part is how this radiation changes our question. Before it, people could debate whether the universe began hot and dense, or whether the universe had always existed in a nearly unchanging state. But the existence of a thermal radiation background covering the whole sky, with a spectrum very close to that of a black body, fits powerfully with a universe that was once hotter and denser. It is not light emitted by separate scattered sources like stars or galaxies. It has the properties of radiation that was once in thermal equilibrium with matter in the early universe. As the universe expanded, that radiation cooled, but it still preserved the fundamental trace of its hot, dense origin. This is why it is not a side discovery, it is a pillar. From the point of view of the one key takeaway, the cosmic microwave background is like a constant reminder that the Big Bang was an event of the entire observable space, not an explosive accident at one location. That light was not thrown outward from a central sphere. It was released when every place in the early universe became cool enough for neutral atoms to form. Every direction in the sky is a line of sight back to the same ancient era. When we look in one direction, we see ancient light from the region of the early universe in that direction. When we look in another direction, we see ancient light from the region of the early universe in that other direction. Every direction speaks of a universe that was once opaque and then became transparent. No direction has a monopoly on being the place where everything began. There is a very important difference between light coming from every direction and light coming from everywhere at the same time in everyday language. The light we receive today comes from a very distant layer of the past surrounding our observable region. But in the early universe, the process that released light happened everywhere when the temperature and density conditions allowed matter and radiation to separate. So the background radiation is not a material shell exploding outward. It is leftover light from the moment the universe changed state. It is like a room full of fog gradually becoming clear everywhere, so light from different regions can suddenly travel farther. But here, the room is not a space that already existed outside the universe. The room is the expanding space of the universe itself. If we want a very slow image, imagine an ocean of hot milk covering everything, so dense that light cannot travel straight. Every ray of light is deflected, blended into the medium, unable to follow a long, free path. Then that ocean gradually cools. The particles that once blocked light combine into a more neutral state. The medium becomes clearer. Light is no longer trapped in the dense dance of collisions. It leaves, but it does not leave from a central island. It leaves from every region of the ocean. And as billions of years pass, expansion stretches that light into faint microwaves. This image is not perfect, but it helps us avoid the old mistake. There is no bomb sitting in a dark sea. There is a universe-wide medium-changing state as it expands and cools. Missions that measured the cosmic microwave background have made this story more precise with each generation. The Cosmic Background Explorer satellite helped measure the spectrum of the background radiation and detect extremely small anisotropies. Later, the Wilkinson Microwave Anisotropy probe mapped the entire sky with greater precision, revealing subtle temperature variations. The Planck Space Telescope from the European Space Agency continued the mapping in even greater detail, helping measure cosmological parameters with high precision. Those maps, seen by the eye, may look like an oval filled with patches of colour. But beneath the colours is data. Places slightly warmer, places slightly colder. The pattern of primordial fluctuations, and numbers that allow the model of the universe to be tested rigorously. We need to be clear. The colours in those maps are usually enhanced in contrast so human eyes can see the differences. The real background radiation is extremely uniform. Without magnifying the tiny differences, we would see almost a smooth background. This makes it even more remarkable. The early universe was even enough for us to say it was homogeneous on large scales, yet rippled enough to create structure. Too uniform and there would be no seeds for galaxies. Too chaotic, and the universe might not have developed into the web of structure we observe. This delicate balance does not need to be mystified. It only needs to be seen correctly. Within the ancient light, there is both regularity and the seed of complexity. Those tiny ripples also help us understand why the expansion of space is not an abstract story. If space were only a motionless stage, the background radiation would have a hard time carrying the traces we observe in the context of a universe, evolving from hot and dense to cold and thin. But when we place it inside an expanding universe, we have a clear logical sequence. The young universe was hot and opaque. The universe expanded so it cooled. Electrons and protons combined into neutral atoms. Light escaped constant scattering. Space continued to expand. The wavelength of light continued to grow longer. Today, we measure that layer of background radiation in the microwave range. That sequence does not need a center of explosion. It needs a history of all space. And that is why, whenever we say, the oldest light, we should not imagine a first lamp located somewhere far away. The cosmic microwave background is the farthest light into the past that we can directly study using electromagnetic radiation, because before the universe became transparent, light could not travel freely to us in a way that preserved direct information. It is like the final curtain of light. Behind that curtain, we can still infer things through physics, through primordial nuclei, through fluctuations, through models, and perhaps in the future through other signals such as primordial gravitational waves, if they are clearly detected. But for light, the cosmic microwave background is the deepest boundary we can directly see. It is the horizon of optical memory. The original question now becomes much deeper. If the Big Bang was an explosion, why does its afterglow not come from one side? Why does it surround us from every direction? The answer is not that we happen to be sitting exactly at the center of a perfect exploding sphere. The answer is that the exploding sphere model is not the right frame. The background radiation covers the sky because it is the trace of a universe-wide stage, when space was still hot and dense and then became transparent. We are inside that universe, not standing outside watching an explosion. Every deep line of sight takes us back to a shared era of space. So the sky is not only the sky, it is the inner face of the deepest past that light can still tell us about. This also means the idea of the echo of the Big Bang must be understood correctly. Saying echo is a beautiful image, but it should not make us think of explosive sound ringing through empty space. The cosmic microwave background is not a sound wave that ears can hear. It is electromagnetic radiation, in the same family as visible light, radio waves, infrared radiation, ultraviolet radiation, X-rays, differing only in wavelength and energy. In the early universe, there were pressure waves in the photon-baryon plasma, and those oscillations left marks in the background radiation map. But what we measure today is not a sound. It is light cooled by expansion. So if we use the word echo, we should understand it as an echo in the sense of physical memory, not sound in the everyday sense. A thoughtful listener may ask, if that ancient light comes from every direction, why is the night sky not blazing bright? This question touches on a deep issue about the history of the universe. The background radiation really is everywhere, but it has been stretched into the microwave range and has a very low temperature. Human eyes are not sensitive to microwaves, so we do not see it as white light covering the sky. Radio and microwave instruments are needed to detect it. The darkness of the night sky to our eyes does not mean the universe is empty of information. It only means that the oldest part of that information lies outside the range of human vision. If our eyes could see microwaves in the right way, the entire sky would have a very faint, almost uniform glow, an ancient layer of light coming not from stars, but from the childhood of the universe itself. That truth has a very quiet beauty. Even in a silent room, when every device is turned off and your eyes are closed, the cosmic microwave background is still passing through the space around you. It does not care about borders, cities, languages, or our personal lives. It is part of the cosmic environment. Those photons have travelled through billions of years of history. While stars were born and died, galaxies merged, planets formed, continents drifted, life appeared, and eventually brains came into being that could ask questions. They do not carry an intentional message, but their existence itself is a natural message. The universe has a hot, dense past, and that past is not located in some distant corner. It covers every direction. But we must keep scientific calm. The cosmic microwave background does not answer every question about the absolute beginning by itself. It does not allow us to look directly at the very first moment. It allows us to look back to the time when the universe was a few 100,000 years old when light was released. Before that, we infer through theory and indirect traces. This is very important. A scientifically careful script should not say that we have seen the moment of the Big Bang through a telescope. We see light from a very early stage after the universe had already gone through a period of development. From that light, together with other evidence, we build the picture of a hot, dense, expanding universe. This humility does not make the model weaker, it makes the model more trustworthy. When scientists analyze the background radiation, they are not simply admiring a beautiful picture. They measure its energy spectrum, its temperature distribution across the sky, its polarization, and its patterns of fluctuation at different angular scales. These details help test the standard cosmological model, including ordinary matter, dark energy, the curvature or flatness of space on large scales, and traces that may relate to a very early period of inflation. We do not need to go deeply into the mathematics. We only need to understand the core idea. The cosmic microwave background is not a decorative image for the Big Bang story. It is a precise data set, an ancient map that helped turn cosmology from philosophical speculation into a science of measurement. And when measurement turns a great question into data, the story changes completely. We no longer ask, how did the universe begin, only through imagination. We ask, what is the temperature of that thermal background? How uniform is it? How large are the tiny ripples? How are they distributed? And do they fit a universe expanding from a hot, dense state? Each question can be answered through measurement, with uncertainty, with testing, with debate, and with independent data. This is how science approaches the things that seem farthest away, not with a loud voice, but with small numbers measured very carefully. From that point, we can understand why the cosmic microwave background is evidence against the image of the Big Bang as an ordinary explosion. An ordinary explosion creates local chaos, with a center, a direction, an inner region, and an outer region. The background radiation, however, shows that the early universe on large scales was highly uniform in every observed direction. The tiny ripples do not break this. They add to it. They do not say, there was a center of explosion. They say, there were small density differences inside an almost uniform early medium. Those differences grew through gravity and created structure, but the overall background still reveals a universe-wide stage, not a local explosion. If we return to the image of a person standing in fog, the background radiation is like the moment when the fog has just cleared enough for us to receive light from the farthest boundary we can see. But the fog did not clear from a central lamp. It cleared according to the physical conditions of the entire medium. When the medium became transparent enough, light from every direction could reach us. In the universe, those conditions were the combination of falling temperature, electrons being captured into atoms, and a sharp drop in the density of free charged particles. This brings us once again back to the central message. The Big Bang was not matter exploding outward into space. It was a history in which space itself expanded, causing the universe to cool, change state, and release ancient light across the whole sky. Perhaps the quietest thing in this entire story is that this ancient light does not need to become dazzling in order to matter. It does not compete with the beauty of a spiral galaxy or a colourful nebula. It is almost monotonous. It is faint. It is cold. It is not appealing to the human eye unless it is translated into a colour map. But that very monotony is the strong evidence. A background radiation that is nearly uniform in every direction is exactly what a hot, dense, expanding universe predicts naturally. It is the beauty of precision, not the beauty of spectacle. It reminds us that sometimes the deepest traces of the universe are not found in the brightest things, but in signals that are very small, very even, and very patient. And from that light, we also learn a lesson about time. When we look at a nearby star, we are looking into the past by a few years or a few dozen years. When we look at a distant galaxy, we are looking into the past by millions or billions of years. But when we measure the cosmic microwave background, we are touching an era before even the first starlight. It is a kind of memory that belongs to no star. It belongs to the universe itself before bright structures existed. So the background radiation is not only evidence of a hot past, it is the emotional boundary of scientific imagination. Beyond it, light no longer tells the story directly in the same way. We have to listen through equations and other indirect traces. If viewers remember only one thing from this section, let it be this. The cosmic microwave background is not smoke drifting out from an explosion point. It is ancient light released everywhere when the early universe became transparent. It comes from every direction, because the Big Bang, in the modern model, was not an explosion inside a pre-existing emptiness. It was the history of space itself expanding from a hot, dense state. And the tiny ripples in that light are the seeds of all later structure, not random fragments of a cosmic bomb. From here, the picture begins to become more continuous. Redshift shows us that space is expanding. The cosmic microwave background shows us that the universe was once hotter and denser, then became transparent as it cooled. The tiny ripples in the background radiation show us how large structures could begin from very small differences. All of these pieces point in the same direction, not toward a center of explosion in space, but toward a universe with a history in which space, light, matter, and time evolved together. And when we place each piece in its proper position, the question, was the Big Bang an explosion in space, is no longer vague. We have evidence to say that image is too small, too mechanical, too much like everyday life. The universe did something deeper. It did not merely throw matter far away. It expanded the very distance between faraway regions, cooled ancient light, and left a map of the universe's childhood across the sky. From that ancient light, we can begin to trace a very long timeline. But before we do that, one thing needs to be made very clear. Science does not pretend to know everything. A careful astronomer will not say they have seen the moment of absolute zero through a telescope. They will say something calmer. These are the traces left behind. This is the model that best explains those traces, and this is the region of darkness where our current equations still do not provide enough light. The closer we move toward the first moment, the more careful our understanding must become. Not because science is weak, but because science is honest. It knows how to distinguish between what has been measured, what is strongly inferred from evidence, and what still lies at the edge of understanding. When we say Big Bang, we should not imagine a cosmic clock beginning with an explosion inside an empty room. A more accurate way to say it is this. If we rewind the expansion we observe today, the observable universe was once in a hotter, denser state, and the distances within space were once much smaller. But the question, what came before that, cannot be answered with easy confidence. There may be models that discuss a stage before the hot, dense state. There may be hypotheses about cosmic inflation, quantum gravity, and deeper states of space-time, but those questions are still being studied. What we can say with more confidence is this. The evidence we have today shows that the universe passed through a very hot, very dense stage and then gradually cooled as space expanded. That sounds simple, but it changes the entire picture in our minds. An ordinary explosion begins in one place, and then matter flies outward into the surrounding region. But the cosmic timeline is not like that. It is not the story of fragments flying across a stage that already existed. It is the story of the stage itself changing size and state. As space expands, the average temperature of the universe drops. As temperature falls, matter can exist in new forms. Each stage in the history of the universe is like a door that opens only when the universe has cooled enough. Too hot, and atoms cannot remain stable. Too hot, and nuclei have difficulty existing in the familiar way. Too hot, and light is trapped in a sea of charged particles. Only when the universe expands and settles down can more stable forms of matter appear one after another. At very early times, the universe did not resemble anything in everyday life. The temperature and density were so high that familiar ideas like rocks, gas, stars, planets, or even atoms had no place yet. According to current understanding, during the early stages, the universe contained elementary particles and radiation in a hot, dense environment. As expansion continued, conditions changed. Some particles became more stable. Physical processes unfolded according to laws that could leave traces we can still detect today. We do not need to turn that stage into a loud spectacle. The truth is already powerful enough. The entire observable universe was once in a state where matter, light, and space did not yet have the calm appearance they have today. Then, as the universe cooled further, light nuclei began to form. This was a very important stage, because it helps explain why the universe contains so much hydrogen, a large amount of helium, and a very small fraction of other light elements such as deuterium and lithium. Heavier elements such as carbon, oxygen, iron, and the elements needed for rocks, water, and living bodies would mostly have to wait for later generations of stars. That means the early universe did not immediately contain the full periodic table we learn about in books. It began much more simply. The chemical richness of the universe is the result of time, stars, gravity, nuclear reactions, and the cycles of birth and death among generations of stars. And here, once again, the one key point returns very clearly. If the Big Bang were only an explosion in space, we might imagine matter being thrown outward, and the story would mostly be about which fragments flew faster and which fragments flew slower. But the real history is deeper than that. The universe did not merely scatter matter, it changed the conditions that allowed matter to become new forms. The expansion of space caused the temperature to fall. That drop in temperature allowed light nuclei to form, then later allowed neutral atoms to appear, and after that allowed gas to gather into stars. An ordinary explosion only heats matter and throws it outward. But the expanding universe opened a sequence of phase changes in reality. About 380,000 years after the early hot, dense stage, the story reaches the moment we have just discussed. Light became free. Before that, the universe was like a hot plasma fog, where photons were constantly scattered by free electrons. When the temperature dropped enough, electrons combined with nuclei to form neutral atoms. The universe became more transparent. Light began to travel freely through space. Today, that light has been stretched into the cosmic microwave background. It is a milestone in the timeline, not because that was when the universe began, but because that was when light began to tell its story directly to us. After that moment, the universe entered a very strange period, the Dark Ages. Dark not because there was no ancient light. The background radiation still existed, but it was cooling and sliding out of the range of visible light. Dark because there were no stars yet. There were no giant nuclear furnaces igniting inside clouds of gas. There were no bright galaxies like cosmic cities. At that time, the universe contained gas, mainly hydrogen and helium, along with dark matter playing an important gravitational role in pulling ordinary matter together. The tiny density ripples once imprinted in the background, radiation began to grow slowly. Regions that were slightly denser pulled in more matter. Matter pulled in more matter. Gravity worked in silence, needing no light, no sound, only time. What is worth noticing is that those dark ages were not a meaningless gap in history. They were like a long night before dawn. There were no stars to shine, but inside that darkness structure was being prepared. Regions of gas gradually fell into deeper gravitational wells. The first clouds began to compress. When gas became compressed enough, the temperature at the center rose. And then, after tens to hundreds of millions of years, the first stars began to burn through nuclear fusion. We do not know every detail about this first generation of stars because they disappeared long ago and direct observation is extremely difficult. But according to current models, they may have been very massive, very hot, and very different from the common stars we see today. When the first stars lit up, the universe did not merely gain more light, it gained a new mechanism for creating complexity. Inside stellar cores, hydrogen fuses into helium, and in later generations of stars, heavier elements are produced. When massive stars die, they can throw the material forged inside them back into space. From then on, later generations of gas clouds are no longer made almost entirely of primordial hydrogen and helium. They also contain carbon, oxygen, silicon, iron, and many other elements. In this way, cosmology connects to chemistry. Chemistry connects to planets. Planets connect to life. But that entire chain could unfold only because the universe had cooled for long enough through the process of expansion. If we stop only at the birth of stars, we still have not seen the full meaning of this for the question of the Big Bang. The important point is that every step in this timeline needs no center of explosion. Light nuclei formed throughout the early universe in general, not inside a fireball located in one corner of space. Ancient light was released everywhere when the universe became transparent, not from a central point of light. The first stars formed in slightly denser regions of matter inside an expanding universe, not from fragments flying outward in one single direction. This timeline is the history of changing physical conditions throughout the entire observable space. It is a slow music of cooling, gathering, lighting up, and becoming more complex. Then the first galaxies began to form. They did not appear as complete spiral shapes from the start. They grew through gas gathering, star formation, collisions, and mergers. Galaxies are not stones thrown out from the Big Bang and then preserved in the same shape. They are physically dynamic systems. Gravity pulls matter inward, gas cools, stars form, stars die, gas becomes enriched with elements, and the cycle continues. To look at a distant galaxy is to look at one stage of that process in the past. To look at many galaxies at many different distances is to read different pages in the history book of the universe. And as modern telescopes look deeper into the early era, the story is still being clarified. New observations of very distant galaxies show that the young universe formed structure quickly and richly in some cases, more than people once expected in simpler models. But that does not mean the Big Bang model is being replaced by the image of a classic explosion. On the contrary, it makes the story of evolution after the Big Bang richer in detail. Scientists adjust models of galaxy formation, examine the roles of dark matter, gas, stellar feedback, supermassive black holes, and many other processes. The big picture remains. The universe was younger, hotter, and denser, then expanded, cooled, and gradually created structure. We can view this timeline as the process by which the universe learned to become transparent, then learned to become bright, then learned to become chemical. At first, light could not travel far. Later, light became free. At first, there were no stars. Later, the first stars appeared. At first, matter was chemically simple. Later, stars produced more elements. At first, there were no rocky planets. Later, dusty disks around young stars could form planets. Each step depended on the step before it, and all of those steps needed time, expanding space, falling temperature, and gravity quietly gathering matter together. The strange thing is this: we do not merely live after the Big Bang, we're made from its history. The hydrogen in water has origins very early in the history of the universe. The carbon in our bodies was made in stars. The oxygen in our breath, the calcium in our bones, the iron in our blood, all belong to a history longer than any civilization. But we must understand this scientifically, not mystically. The body is not a direct fragment of a cosmic bomb. The body is the late result of a universe that expanded long enough, cooled long enough, formed stars long enough, enriched itself chemically long enough, and formed planets long enough for matter to arrange itself into more delicate structures. If the universe did not expand, the story would be completely different. If it had always remained too hot, atoms could not exist stably. If light had remained forever scattered in plasma, the universe could not have become transparent as it is today. If there had been no tiny density ripples, matter would have had difficulty gathering into stars and galaxies. If there had been no stars, heavier chemistry would not have been produced in abundance. So the expansion of space is not just a background detail in cosmology. It is the condition that allowed matter to change over time. It is the reason the universe could move from hot and dense to transparent, from dark to bright, from simple to complex. Here, we also need to avoid another misunderstanding. When we say the universe cooled, do not imagine it cooling like a hot object placed in a cold room. There is no outside room for the universe to transfer heat into. The cooling of the universe is connected to the expansion of space itself. Radiation has its wavelength stretched. The density of matter decreases as the volume of the observable universe increases in the appropriate way. This is completely different from an explosion in air where hot gas spreads into the surrounding environment. The universe does not need an outside in order to cool. It cools because the geometry of space itself is changing. When we place each milestone in the right position, the timeline becomes an argument. The hot, dense universe is not an isolated hypothesis. It explains why there is a cosmic microwave background. It is connected to the proportions of light elements. It fits the expansion observed through redshift. It allows us to understand the formation of structure from early ripples. It opens the story of stars, galaxies, planets, and eventually observers. If the Big Bang were a local explosion, it would be much harder to build such a unified chain of explanation. But if the Big Bang was the hot, dense stage of the entire observable universe inside expanding space, then the pieces of evidence begin to fit together. And for that same reason, when we talk about before the Big Bang, we should lower our voices. There are very deep questions here. Did time begin together with the hot, dense stage? Or is the hot, dense stage only the earliest part that our current model can describe reliably? Was there an extremely rapid period of cosmic inflation before that? And if so, what exactly caused it? Do the familiar laws of physics still hold when energy becomes extremely high? These questions should not be covered over with a story that sounds too easy. A good scientist is not afraid to say, "We do not fully know yet." That sentence keeps imagination from running beyond the evidence. But that uncertainty does not make the part we do know vague. We do not need to know everything about the very first moment to understand that the image of an explosion in space is misleading. We may not know the deepest nature of the extremely early moment, but we know the universe is expanding. We know the cosmic microwave background exists and covers the sky. We know the universe was once hotter and denser. We know ancient light was released when the universe became transparent. We know large structures formed from tiny density differences through gravity. Those facts are enough to change the fundamental picture. Not matter exploding into a pre-existing emptiness, but space and matter sharing a history of evolution. Today, when we say the universe is about 13.8 billion years old, we're talking about the age of the universe in the standard cosmological model based on current evidence, especially expansion, the cosmic microwave background, and observations of large-scale structure. That number is not a number measured by a clock placed beside the Big Bang. It is inferred from many layers of data and physical models. So it is both very strong and deeply tied to how science works, measuring, testing, improving, and understanding uncertainty. Data from missions such as Planck have helped measure cosmological parameters with high precision, including the age of the universe and the composition of its matter and energy. And at the end of that timeline is something very quiet. Humans look back. Not from outside the universe, not from a central position, not like an audience member standing outside a theatre watching an explosion on a screen. We look back from inside the very universe that produced the conditions for us to exist. A telescope is the eye of matter looking back into the past of matter. Mathematics is the way a brain, made from atoms forged in stars, describes the expansion of space. When we understand the Big Bang more correctly, we're not only correcting a false image, we're learning our true position, not at the centre of an explosion, not outside the story, but inside a very long cosmic history, where space expanded long enough for light, stars, chemistry, and consciousness to appear together. So the timeline of the universe is not a chain of isolated events. It is a slow answer to the original question. Was the Big Bang an explosion in space? No. If it were an explosion in space, we would search for a centre, an expanding edge, an outside environment, and a stream of fragments. But the real timeline shows something else. The entire observable universe was once hot and dense, space expanded, temperature fell, light nuclei formed, atoms appeared, light became free, darkness lasted, the first stars ignited, galaxies grew, heavy elements were created, planets formed, and after 13.8 billion years, a small part of the universe could ask how it began. That was not the sound of matter exploding inside a room. It was the history of the room itself expanding. If we go to the end of that timeline, the original question returns in a sharper form. So where did the Big Bang happen? This question sounds very natural because almost every everyday experience we have connects events with locations. A glass falls on a table, a storm forms over the ocean, a volcano erupts at a crater, an explosion happens at one position and then spreads outward. But with the Big Bang, if we use that same habit, we are led into the wrong picture. The most accurate answer is not very far away, nor at the centre of the universe, and certainly not at some point beyond the reach of telescopes. The deeper answer is this: the Big Bang happened everywhere. Not because it spread to every place like fire spreading across a field, but because every place today in the observable universe was once part of the original hot, dense state. This needs to be heard slowly. When we say the Big Bang happened everywhere, we do not mean there was an explosion at every point in space, like billions of tiny fireworks. We also do not mean that an explosive centre sent a wave of fire across the universe until it covered everything. The right idea is this: the places we now call here, over there, toward that distant galaxy, toward that very distant galaxy cluster, all belong to the same universe that was once hotter, denser, and had smaller distances in the past. If we rewind the expansion, we do not trace galaxies back to a point located somewhere in the present sky. We trace the history of all observable space back to an earlier state of itself. This is why the question, where was the Big Bang, is like a doorway into a new way of thinking. If we ask it as an address, as though asking which street corner an explosion happened on, we have already placed the question in the wrong frame. The Big Bang was not a local event happening inside a universe that already existed. It was not like a stone thrown into a pond, creating ripples that spread out from one central point. It was more like a change in the entire surface of the water, if the entire surface of the water had its own history of expansion. But even that image is only a metaphor. The point to keep is this: there is no privileged point in space today that we can call the place where the Big Bang went off. Every deep direction we look takes us back to a shared era of the young universe, not to a single mouth of explosion. Perhaps this is the hardest part, because our imagination loves to stand outside and observe. We want to step outside the universe, look at it like a sphere, and ask where it is located, what it is expanding into, and where its centre is. But science does not give us that outside position in observation. Every measurement we make is performed from inside the universe. Every photon arriving at a telescope has travelled through the space of the universe. Every equation that describes expansion also describes the geometry from within, without requiring a larger room surrounding it. So when we imagine the universe as an object swelling into an empty space outside itself, we have accidentally carried an everyday image into a place where it no longer fully applies. The balloon image is often used to help people understand this idea, but it must be used very carefully. Imagine that there are only beings living on the surface of a balloon, knowing nothing about the inside or the outside of the balloon. As the balloon is inflated, the distance between points on the surface increases. A being at any point sees more distant points moving away. But on that surface, no point is the centre of the expansion. The centre of the balloon lies in the three-dimensional space outside the surface, not in the two-dimensional world of those beings. This example helps us understand one thing: a space can expand without having a centre located inside that space itself. But we should not understand the universe as exactly like a balloon. A balloon has rubber. A balloon has air outside it. A balloon has someone blowing it up. Modern cosmology does not simply say the universe is a balloon swelling inside a larger room. The balloon example only helps untie one knot in our intuition. Expansion does not have to have an internal centre. When the space between galaxies increases, that does not require an outside like the air around a balloon. In general relativity, space and time are part of the geometry of the universe. Expansion is understood as a change in that geometry over time, not as matter pushing into a pre-existing emptiness. From that seemingly simple point, the story begins to open into a deeper layer. If space is not expanding into a larger room, then the question, what is outside the universe, must be asked very carefully. The whole universe may be much larger than the part we can observe. It may be infinite. It may be finite, but without a boundary in the intuitive sense, like the surface of Earth, which has a finite area, yet you can keep travelling without reaching an edge where you fall off. These possibilities belong to the geometry and global structure of the universe, and science continues to study them. What matters for our question is this: the expansion we observe does not require an explosive edge or an outside space for matter to fly into. Another way to see the issue is to distinguish between the observable universe and the entire universe. The observable universe is the region from which light has had enough time to reach us since the earliest stages that can be observed with light. It has us at the centre in an observational sense, like a person standing in fog is at the centre of the region they can see. But that does not make us the true centre of all reality. An observer in a distant galaxy would also have their own observable universe. They would also see the background radiation surrounding them. They could also infer a hot, dense past. That does not create many different centres of explosion. It shows that there is no centre of explosion in the usual sense. So when we ask where the Big Bang happened, the answer, everywhere, is really a way of correcting the imagination. It tells us not to look up at the sky searching for some faraway place where everything began. The place where you are right now, if rewound far enough through cosmic history, also belonged to that hot, dense state. Not because this room existed as it is today in the early universe, not because Earth was present from the beginning, but because the region of space and matter that later contributed to the environment around us was also part of the same history of expansion. The deepest past is not located at a distant coordinate. It lies in the history of every coordinate. Perhaps we should hear the words Big Bang not as a sound, but as a historical symbol. It was not a blast echoing through darkness. It is the name we give to the period when the universe was hotter, denser, younger, and began the story of expansion that continues to this day. That name is powerful and easy to remember, but it can also mislead the imagination. Bang makes us think of sound, but sound needs a medium to travel through. It needs pressure waves moving through matter. It needs an ear or a device to detect it. The Big Bang was not a blast that someone outside the universe heard. There was no outside audience. There was no empty cosmic atmosphere for sound to echo through in the ordinary way. That does not mean the early universe had no oscillations at all. In the hot plasma of the young universe, there were very real density and pressure oscillations, and their traces are still imprinted in the cosmic microwave background. But calling that a bang in the sense of a loud sound in space leads to misunderstanding. What we call the Big Bang is not a sound. It is a model of the early state and evolution of the universe. It says the universe expanded from a hot, dense stage, not that a cosmic bomb made a noise in an empty region. If there is any music in this story, it is the music of physical oscillations, of stretched light, of measured numbers across the sky, not the boom of an exploding firework. And once we understand this, the whole picture begins to change. The old questions do not disappear, but they become more precise. Instead of asking, where did the Big Bang explode, we ask, why were all regions of the observable universe once hot and dense? Instead of asking, what did it explode into, we ask, what geometry describes the expansion of space? Instead of asking, where is the center, we ask, why do observations show that the universe is nearly homogeneous and isotropic on large scales? Science does not only give us answers, it teaches us to reshape the questions so they do not carry false assumptions. Even so, some mysteries still stand at the edge of the story. What existed before the hot, dense stage that we commonly call the Big Bang? That question is fascinating, but it is also very difficult. If time, as we understand it, is deeply tied to the evolution of the universe, then before may not be as simple as yesterday coming before today. In some ways of understanding it, asking what came before the Big Bang may be like asking what is north of the North Pole. But not all scientists express the issue in the same way, and many theoretical models are still trying to explore deeper possibilities. The most honest thing to say is this: we do not yet have a final answer. Another mystery is cosmic inflation. Many models suggest that, in the extremely early moments, the universe may have gone through a period of extraordinarily rapid expansion, helping explain why the cosmic microwave background is so uniform across distant regions of the sky, and why space on large scales appears very close to flat. This idea is very powerful in modern cosmology, but the deepest physical details of inflation are still being studied. What was the exact mechanism? What physical field caused it? Are there remaining traces we can measure more confidently? These questions are still open. They remind us that even though the hot, dense, expanding model is very strong, the earliest part of the story still contains layers of fog that have not yet cleared. Whether space is finite or infinite is also a major question. The observable universe is certainly finite in the sense that we receive light only from a limited region, but the whole universe could be far larger and may even be infinite. If it is finite, it may have no edge like a final wall. If it is infinite, then the Big Bang still was not an explosion from a tiny point inside infinite space. In the expansion model, an infinite universe could also have once been hot and dense everywhere, then expanded in the sense that distances between points increased. This sounds paradoxical to intuition, but it shows why we should not force the universe into the image of a small sphere swelling in the dark. Another question is this: was the Big Bang the absolute beginning, or only the boundary of our current model? This is where science must speak with humility. The equations of general relativity, when rewound to extreme conditions, suggest a singular state in the classical model. But many physicists think that at extremely high energies and densities, quantum effects of gravity may become important, and the classical model may no longer be enough. So the first moment may be where our current theory reaches its limit, not necessarily a complete picture of reality. This does not make the Big Bang disappear. It only reminds us that the Big Bang, in the best scientific sense, is a very strong model of a hot, dense, expanding universe, while the deepest nature of the beginning still needs more understanding. Unanswered questions do not make science weaker, they make science more honest. A truly vast universe does not need us to understand everything in a single night. In fact, those limits make the story more trustworthy. If someone says they know for certain everything that happened before time, before space, before any possible testable observation, we should be careful. Good science says, this part is strongly supported by evidence, this part has good models but still needs testing, and this part we do not yet know. In that distinction there is a very quiet beauty, the beauty of intelligence that does not rush. And so, the final answer to where did the Big Bang happen is not a coordinate, it is a way of understanding. It happened everywhere in the sense that the entire observable universe was once in a hot, dense state. It didn't happen inside a pre-existing space, because space itself is the part expanding in the story. It did not explode into a larger room, because the model does not need that room in order to describe the observations. It has no center like a firework, because observers everywhere on large scales can see a universe expanding around them. It was not a sound, but a historical name for a young, hot, dense universe that expanded and cooled. If we need one final image for this section, let us not choose a bomb. Let us choose a map whose scale changes over time. The cities on the map are not running on their own feet. The distance between them grows because the scale of the map itself is stretching. But even that image is only a temporary bridge. The universe is not paper. Space is not printed ink. What matters is that we have left the false picture behind. No object exploding into emptiness, no single center, no edge of fire spreading outward. In its place is a universe with a geometric history, where distance, light, matter and time change together. When we look back across the whole journey, we see the pieces fall into place. Redshift tells us that the space between distant galaxies is expanding. The cosmic microwave background tells us that the universe was once hotter, denser, and then became transparent. The tiny ripples in the background radiation tell us that cosmic structure began from very small differences, not from fragments of a chaotic explosion. The cosmic timeline shows that matter could become atoms, stars, galaxies, planets, and life only because expanding space changed the conditions. All of it serves one message. The Big Bang was not an explosion in space. The Big Bang was the early history of space itself expanding. And perhaps what makes this idea most beautiful is that it brings the beginning closer than we think, but not in a mystical way. The Big Bang did not happen somewhere so far away that it has nothing to do with us. It also did not happen right inside this room in the everyday sense of an object. Rather, the region of space and matter that led to this room, this planet, this body, this light, all belonged to the same history of expansion. We do not stand at the center of the universe, but we also do not stand outside the story. We are a very late, very small, very fragile part of a process that has stretched from the time when the universe was hot and dense to today. So when night falls and the sky seems still, that stillness is not empty. In that darkness there is ancient light that has cooled. In the distance between galaxies there is the trace of expansion. In the atoms of the body there is the history of stars, and inside the question, where did the Big Bang happen? If we listen long enough, there is a gentler answer. Not in some faraway place, not at a secret center, not inside a cosmic room that already existed. The Big Bang, in the modern understanding, belongs to every place in the observable universe, because it is the very hot and very dense first chapter of space itself expanding. So after a long journey, we can set the original question down very gently. Was the Big Bang an explosion in space? The answer, according to modern scientific understanding, is no. It was not a cosmic bomb exploding in the middle of darkness. It was not a central point shooting galaxies in every direction. It was not a fire spreading into a space that already existed. The Big Bang is the name we give to a very early stage when the universe was hotter, denser, younger, and space itself was expanding. Tonight we have passed through the quiet but powerful traces of that story. Light from distant galaxies shows that cosmic distances are growing larger. The cosmic microwave background shows that the universe was once hot and dense, and then became transparent enough for light to travel freely. The tiny ripples in that ancient light became the seeds of galaxies, stars, planets, and eventually minds capable of looking back up at the sky. Every piece of the puzzle says the same thing. The beginning we call the Big Bang is not located in some faraway place, but belongs to the history of all observable space. Perhaps the deepest beauty of this truth is its quietness. The universe did not need to begin with a thunderous explosion in order to be majestic. It could begin in a state that our language can only partly touch, and from there, space expanded, light cooled, matter settled, stars were born, and time slowly shaped things into greater complexity. Now, let that thought settle with your breath. Out there, space is still expanding in silence. Ancient light is still drifting across the sky. And we, in one small moment of cosmic history, have been allowed to understand a little more about where we belong. Sleep well. I will see you again on the next journey as we continue listening to the universe tell its own story.